Have you ever looked at one of those giant container ships stacked to the sky with cargo and just thought, how? How does that not just fall over? Well, today we're pulling back the curtain on the invisible physics that keeps these behemoths afloat and upright. Seriously, it's a great question. It almost feels like it shouldn't work, right? But what's really going on is this constant, high-stakes battle between some massive forces. And figuring out how that battle is won is an absolute masterclass in engineering. So let's break it down. Okay, so the whole fight for balance really starts with two fundamental forces. These two are always at play when you put anything in the water. They are the main contenders in our story. First up, we've got the center of gravity. We'll just call it G. I want you to picture a single imaginary point where the entire weight of the ship, we're talking the hull, the engines, every single container, is all concentrated. It's the point that gravity is pulling straight down towards the center of the Earth. And pushing back against that massive downward pull is the center of buoyancy, or B. This is basically the water's counterpunch. It's the geometric center of the part of the ship that's underwater, and it's the exact point where all the upward force from the water is focused. Now, check this out. In perfectly calm water, everything is in harmony. As you can see here, the center of gravity, G, pulling down, and the center of buoyancy, B, pushing up, are in a perfect vertical line. They cancel each other out, and the ship floats nice and steady. It's a peaceful stalemate. But, the ocean is almost never perfectly calm. So what happens when a wave or a gust of wind knocks the ship and breaks that perfect alignment? Well, this is where the real secret weapon comes into play, this kind of magical, invisible point called the metacenter. So watch what happens when the ship tilts, or as sailors say, it heels over. The whole shape of the underwater part of the hull changes, right? More of it goes into the water on one side. And since the center of buoyancy is the center of that underwater shape, it has to shift sideways, moving over to the side that's now deeper in the water. And this is the light bulb moment. If you draw a straight line vertically up from that new shifted center of buoyancy, it crosses the ship's original center line. And that exact point of intersection, that's the metacenter, or M. It's not a real physical thing on the ship. It's a geometric point that acts like a pivot. And it is everything. So here's the bottom line. The entire battle for balance comes down to where the ship's center of gravity, G, is relative to this new pivot point, the metacenter, M. That vertical distance between them has a name. It's called the metacentric height, or GM for short. And that single value tells you if the ship is going to save itself or capsize. So how does this all play out in the real world? Well, based on that relationship between G and M, there are really only three situations a ship can find itself in when it gets pushed around by the sea. Okay, first up, the one you always want, a stable ship. In this case, you can see the metacenter, M, is high above the center of gravity, G. This creates something called a righting lever. Basically, the forces of gravity and buoyancy create a twisting force, or a torque, that pushes the ship back upright. It literally wants to get back to being level. Now here's the dangerous one. Look how the positions have flipped. G is now above M. The forces now work together to do the exact opposite. Instead of righting the ship, they create a capsizing force that pushes the tilted ship even further over. This is the absolute nightmare scenario for everyone on board. And finally, there's this weird middle ground. This is what happens when G and M are in the exact same spot. There's no force pushing it back upright, but there's no force pushing it over either. The ship just gets pushed to an angle and stays there. It's just sitting there, waiting for the next wave. Yeah, not a great place to be. So, knowing all this, how do ship designers and the crew actually control these forces? How do they make sure the ship always stays in that safe, stable condition where G is kept safely below M? Well, the playbook is actually pretty straightforward. It's all about one goal: lower the ship's overall center of gravity. You can do that by literally moving heavy things from a high deck to a lower one. You can load new, heavy cargo deep down in the hold. Or you can get rid of weight from high up, like discharging ballast water from upper tanks. But here's a fun twist. You can actually have too much stability. If that metacentric height, the GM, is really big, they call the ship stiff. It'll snap back upright super fast and violently after a wave, which can be really uncomfortable and even damage cargo. On the other hand, a tender ship with a small GM has a slow, gentle roll. You want to be somewhere in that Goldilocks zone, right in between. And this is exactly what naval architects design for. Just look at this table. Different ships need different amounts of stability. A massive supertanker needs a huge metacentric height, maybe up to 5 meters, to stay safe. But a smaller cargo ship might only need half a meter. It's all incredibly precisely calculated for each and every vessel.
So there you have it. From the simple act of floating to that complex dance in a storm, it all comes down to this constant invisible battle. A battle between gravity, buoyancy, and that all-important metacenter. And now you know how good design and smart planning make sure the ship always wins. And that kind of makes you wonder, doesn't it? What other hidden forces are quietly shaping the world we live in? What invisible battles are being fought in the design of everything from skyscrapers to airplanes? Something to think about.